Hello, and welcome to the first video for Section 10.2 on Calculus with Parametric Curves. Recall that a parametric curve C is a curve given by parametric equations x equal to f of t and y equal to g of t. It is good to think of C as a curve that is traced out by a moving particle or object. The goal of this section is to do all of the calculus that we did for curves given by equations y equal f of x for parametric curves. This includes finding tangent lines, checking concavity, and finding arc length and areas. Let us begin with finding tangent lines. For this, we assume that C is given by parametric equations x equal to f of t and y equal to g of t, where f and g are differentiable functions of t. At this point, one should note that y is implicitly a function of x, as both y and x depend on t via the equations x equal to f of t and y equal to g of t. Thus, we also make the additional requirement that y is a differentiable function of x. Bearing this in mind, recall the chain rule. dy dt equals dy dx times dx dt. Note that if dx dt does not equal 0, then we can solve for dy dx. We get that dy dx is equal to dy dt divided by dx dt. This equation allows us to find the slope of the tangent line to the curve at a given point in the xy plane. Notice that dx dt does not equal 0, so if dy dt equals 0, then dy dx equals 0. So in particular, the tangent line is parallel to the x-axis, as there is no rate of change happening in the y direction. Thus, whenever dy dt equals 0 and dx dt does not equal 0, the curve has a horizontal tangent. But what happens when dx dt equals 0? If dy dt does not equal 0, then according to the equation dy dx equal to dy dt divided by dx dt, dy dx tends to infinity. So the tangent line is vertical, as there is no rate of change happening in the x direction. If dx dt equals 0 and dy dt does not equal 0, then the curve has a vertical tangent. What happens when both dx dt equals 0 and dy dt equals 0? Then there is no rate of change happening in either the x direction or the y direction. You should think of this as a stationary point. If C is traced out by a moving particle, then at that instant of time t, the particle was motionless. It may have paused to change direction. So here, there could be a vertical or horizontal tangent, or neither. This case usually demands further investigation. Let's do an example. Suppose that you are given a curve with parametric equations x equal to sine of t and y equal to sine squared of t. Observe that y equals sine squared of t, which equals sine of t squared, which equals x squared. So this is the graph of the parabola y equal to x squared. But we have the restriction that negative 1 is less than or equal to sine of t, which is less than or equal to 1. So negative 1 is less than or equal to x, which is less than or equal to 1. So this C is just the piece of the parabola between the points negative 1, 1 and 1, 1. But how is C traced out? Notice that negative infinity is less than t is less than infinity. So as t varies, the particle is moving up and down this piece of the parabola in a pendulum-like motion. We now compute dx dt is equal to cosine of t, and dy dt is equal to 2 sine of t times cosine of t. Notice that when t equals 0, we are at the point 0, 0, and dx dt equals cosine of 0, which equals 1, which does not equal 0, while dy dt equals 2 sine of 0, cosine of 0, which equals 0. So we have a horizontal tangent at the point 0, 0, as indicated by the graph. At t equal to pi over 2, notice we are at the point 1, 1 in the graph. But observe that dx dt equals cosine of pi over 2, which equals 0, and dy dt equals 2 sine of pi over 2 times cosine of pi over 2. So dx dt and dy dt are both 0. As expected, this is a stationary point, as at this point the particle climbed up the parabola, paused to turn around, and moved back down. We now turn our attention to investigating concavity. Recall that the second derivative, d squared y divided by dx squared, measures concavity. Let us compute. Recall that dy dx equals d dx of y, which equals dy dt divided by dx dt. So d squared y divided by dx squared equals d dx of dy dx, which equals d dt of dy dx divided by dx dt. Note that the second equations were obtained from the first equations by switching y with dy dx in the first equation. We take this moment to issue a warning. Notice that d squared y divided by dx squared equals d dt of dy dx divided by dx dt, and that d squared y divided by dx squared does not equal d squared y divided by dt squared, all divided by d squared x divided by dt squared, as you would initially expect. Recall in our previous example that x equals sine of t and y equals sine squared of t, and that we computed dx dt equal to cosine of t and dy dt equal to 2 sine of t times cosine of t. Provided that dx dt equal to cosine of t does not equal 0, we have that dy dx equals dy dt divided by dx dt, which equals 2 sine of t cosine of t divided by cosine of t, which equals 2 sine of t. So d squared y divided by dx squared equals d dt of dy dx divided by dx dt, which equals d dt of 2 sine of t divided by cosine of t, which equals 2 cosine of t divided by cosine of t, which equals 2. This computation agrees with the fact that we are dealing with a piece of a graph of a parabola y equal to x squared, as there d squared y divided by dx squared equals 2.